Welcome to Mr. Frolick's physics classes. In this video, we'll learn about one-dimensional collisions. Hello there. Today we're going to talk about one-dimensional collisions. Collisions in one dimension. As a general idea, a collision is a process where we have a before the interaction, where the two objects are approaching each other. Then I'll have the interaction while they are colliding. And during this interaction, they are exerting their mutual forces. And in general, after the collision, they will move their own ways. Okay? Well, while they are colliding, they suffer deformations. And this video from the golf ball being hit by a club that I downloaded from YouTube is a good example of it. You see that every time an object is under the influence of a force, it will suffer a deformation. Now, the general kind of collision that we're going to have will depend on this kind of deformation that the object has. So, if my object is elastic, and elastic means it behaves like a spring, so it's in a spring-like object, the energy that goes into changing the shape of the object is retrieved back when the object springs back to its original shape. So an elastic kind will conserve kinetic energy. A non-elastic type, or what we usually call inelastic, will not conserve kinetic energy. The inelastic type could be, for example, the Play-Doh style. Oops, wrong pen. The Play-Doh style. And this one, the energy that goes into deforming the object is not completely retrieved when the object comes back to its original shape. So this one here doesn't conserve kinetic energy. I would also like to call your attention for two things that people often confuse a lot, which I'm going to call stretchability and elasticity. Stretchability is the ability to stretch, to change shape. Examples of highly stretchable materials: rubber bands, Play-Doh, springs, those are highly stretchable materials. But they are not necessarily elastic. Elasticity is the ability to return to its original shape, to get the energy that was done energy was used to do work to change the shape of the object, is returned to the system. And examples of highly elastic materials would be steel and glass. Glass, for example, is a highly elastic material. Marbles that we play with them and bounce them around are really glass balls. So the kind of deformation that the objects suffer will determine for us the kind of collision that we're going to have. But one thing for sure will happen with every single collision, which is this here. The force that the particles exert on each other during the collision is extremely large, is an impulsive kind of force, and is an internal force. So what I'm going to have for all of our collisions all collisions that we will consider, please, the momentum total final will be equals to the momentum total initial. Okay? And we are talking about one-dimensional collisions at this point. We'll see two-dimensional collisions later. Now let's see a little bit more details about the kinds of collisions and the properties that they have. When the two objects that are colliding are elastic, we have what we'll call elastic collision. And in an elastic collision, the objects will approximate each other, collide, and then separate. Okay? And like I said before, in this kind of collision, the total momentum is conserved. Therefore, I can write, so the total momentum initial equals the total momentum final, and then I have that m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. In terms of energy, being an elastic collision means that energy is going to be conserved. Therefore, the kinetic energy total initial equals the kinetic energy total final. And that will give me then that the total kinetic energy initial, 1/2 of m1 v1 initial squared plus 1/2 of m2 v2 initial squared, must be equal to the total kinetic energy final, 1/2 of m1 v1 final squared plus 1/2 of m2 v2 final squared. So these are in principle the two equations that we have to discuss elastic collision. Now let's talk about the inelastic collisions. In general, I'm a little bit lost here with these markers, but in general, as a rule of thumb, with inelastic collisions, we'll have roughly the same situation as the elastic collision. The objects will approximate, collide, suffer some deformation, they retrieve back a little bit, not as much, and then they go their own ways. So at first they look a lot like this here. But in terms of equations, you'll see that there is an important difference. Momentum is still conserved, so I can still write that. The total momentum initial equals the total momentum final. The problem, or the difference, the real difference here, is when it comes to energy. Because energy is lost, I can no longer state that the total kinetic energy is the same. Then what we have is that the kinetic energy total final is going to be less than the kinetic energy total initial. Often, the problems will give us a percentage of energy that is lost, and then you can try to work from there. If you know that 20% of the energy was lost, then you can say that the final energy is 80% of the initial energy. Something like that. There is a very important particular type of inelastic collision, which we call completely inelastic. And I hope I'm spelling completely right. I'm not sure. But the completely inelastic collision. On a completely inelastic collision, the objects crash, deform, and they don't return. They stay stuck. The energy that went into deforming the objects is completely lost. So I want to have a system that would look like this here, perhaps. So the objects approximate each other with velocities v1 initial and v2 initial. They crash, and then they get stuck. And after that, they keep on moving with a total combined velocity v final. Momentum is conserved. And I can write this equation as this way. m1 v1 initial plus m2 v2 initial equals to m1 plus m2 v final. I can factor v out. Energy is also not conserved. But this completely elastic collision problem is the simplest from a mathematical perspective because I can factor out that velocity. I usually have just a simple one unknown. The completely inelastic collision can also be considered as the reverse problem of the explosion, in which I had something that was moving together and suddenly explodes in parts. From a mathematics perspective, I would just be swapping left and right hand sides. In the typical problems we're going to be working with, we know the initial conditions of my problem, but we don't know the final conditions. Meaning, I don't know, for example, the two final velocities. And usually, the equation of momentum is not enough to solve the problem, because I would have one equation and two unknowns. Although we have the equation for kinetic energy available, because it is a quadratic equation, it usually becomes complicated quite fast. It's not a very good tool to handle this. And so we're going to now develop the idea of coefficient of restitution that will help us in dealing with the mathematics of elastic collisions. I will now adopt a reference frame positive in one direction, one dimensional, and I'm going to drop the vector notation. So starting from conservation of momentum, I will transfer everything that depends on 1 to the left-hand side and everything that depends on 2 to the right-hand side. My equation then will become this here. So m1 v1 initial minus v1 final, where I factor out m1, equals to m2 v2 final, which was this term in here, minus m2 v2 initial, which was this term moved to the right-hand side. I'm going to hold this equation here as equation 1. And now, let's work on the equation from kinetic energy, and let's actually start from this equation and do the same thing. Move everything that depends on 1 to the left-hand side, and everything that depends on 2 to the right-hand side. And then this equation can be rewritten as I will start by simplifying the 1/2 everywhere, and then m1 v1 initial squared. On the left-hand side, I had here m1 v1 final squared, goes to the right-hand side, minus v1 final squared, equals to, on the right-hand side, m2 v2 final squared, minus m2 v2 initial squared. Okay? But what I have in here is the difference of the squares. And let's remember that a squared minus b squared is a plus b multiplied by a minus b. So this equation of energy can be rewritten as m1 v1 initial plus v1 final multiplied by v1 initial minus v1 final equals to m2 v2 final plus v2 initial multiplied by v2 final minus v2 initial. And this equation I'm going to call equation number 2. Now, if I divide equation 2 by equation 1, we'll get this here. m1 cancels out. v1 initial minus v1 final cancels out. So on the left-hand side, I have just V1 initial plus V1 final equals. On the left-hand side, I'll have M2 cancel out. And besides that, V2 final minus V2 initial also cancel out. So the only thing we have left over is V2 final plus V2 initial. This equation can be rewritten this way. If I get everything that has to do with final and move the left-hand side, and everything that has to do with initial to the right-hand side, I would have V1 final minus V2 final equals to V2 initial minus V1 initial. At the end of last topic, at the end of last board, we had this equation down here on the bottom right corner. So let's just keep on going from there. I can now divide the two sides by V2 initial minus V1 initial, and that will give me V1 final minus V2 final over V2 initial minus V1 initial equals to 1. This equation here can be understood this way. V1 final minus V2 final is the relative velocity after the collision. And V2 initial minus V1 initial is the relative velocities before the collision. And I get the impression that I got messed up someplace in here, but still it's going to work this way. This here now becomes a very easy and simple equation for us to deal with perfectly elastic collisions. One quick comment I would like to add is this here now. AP exam would either have elastic collision, completely inelastic collision, or they will give you some further information. But in general, this coefficient of restitution could be understood as a measurement of elasticity of the system. And many people define this here as E for elasticity, I guess. It does not really matter how you write this here as long as you keep it 2 minus 1, 1 minus 2, okay? And the completely inelastic collision has a coefficient equals to 0, because after the collision, the two objects move together, their final velocity is the same. The elastic collision has a coefficient equals to 1, which is what we had in here, and a generic inelastic that does not get to be completely inelastic would have a coefficient between these two. And basically, this is it in terms of theory. I think that now we should work a couple problems. So the first problem we're going to solve is the problem represented here on the slide. And it says that a 2 kilogram mass moving to the right at 1 meter per second collides heads-on with a 1 kilogram mass moving to the left at 2 meters per second. And they stick together and they want to know their final velocity of the system. Well, the first thing I want to do is set a reference frame and identify a direction to call positive. So, for example, if I call the right positive, the velocity of the 1 kilogram object should be negative, basically. If now I label these objects as A and B, A and B, I can write my equation of conservation of momentum as this here. MA VA initial plus MB VB initial equals MA plus MB V final. And now it's really just plug in the numbers. So MA is 2. But when we plug in the numbers, we get that the left-hand side of this equation is actually 0. And then that means for me that the final velocity of the system is 0. Their initial momentum was 0. Although they were moving with respect to each other, their final momentum is still 0. Notice that kinetic energy of the system, on this case, was completely gone. It became heat and sound. In our next example, still representing the slide, we have two carts of masses m and m prime who are moving initially with velocities of 60 and 30 centimeters per second. The two carts will couple together. They will move like one with a common velocity of 40 centimeters per second. And the problem asks us to find the ratio m prime over m. Well, to solve this problem, I will just start again from conservation of momentum, and I will say that m times 60 plus m prime times 30 equals. Since I want m prime over m, I know that I'll need to solve for them in separate. I'm going to keep these here as separate things. M times 40 plus m prime times 40. So I'm going to transfer m prime to the right-hand side and m to the left-hand side. So that's going to become then 60m minus 40m equals 40m prime minus 30m prime. Or 20m equals 10m prime, and m prime over m is going to be 2, if I didn't make any silly mistake. The next problem will tell me that we have two spheres, A and B, both of the same mass m. A is at rest, but is mounted as a pendulum to a pin, and it can oscillate freely. B is incoming at 1 meter per second, and they will undergo a frontal elastic collision. The question asks me how many collisions would happen total, and what are the final velocities of the two spheres. Well, the first thing I need to do is determine their velocities after this first collision. So I will now set a reference frame, positive to the right. In that sense, then, velocities to the right are positives, and negative velocities would represent a velocity to the left. Perfectly elastic collision, momentum is conserved. So I can say that total momentum initial equals total momentum final, or MA VA initial plus MB VB initial equals MA VA final plus MB VB final. First, A is initially at rest. Therefore, this term is 0. Second, they have the same mass. So I can quite easily simplify their masses here. I can cut out MB, MA, and MB. And my equation is going to be reduced to VB initial, which was 1, equals to VA final plus VB final. Now, this is the typical scenario I mentioned earlier. I have one equation and two unknowns. I could use a second equation from kinetic energies, but that equation is going to be quite complex for us to handle. Or I can use the coefficient of restitution, which will tell me that VA final minus VB final divided by VB initial minus VA initial equals to 1. Let's remember that VA initial is 0, and VB initial is 1. So this equation here is going to tell me that VA final minus VB final equals to 1. So now I have two equations, 1 and 2. I can make a system of equations to solve them. So 1 equals VA final plus VB final, and also 1 equals VA final minus VB final. And I think that the best solution for this is just to add the two equations. Because when I add the two equations, VB final will cancel out, and what we have at the end is 2 equals to, 2 VA final, and so VA final is 1 meter per second. If now I get this result and bring it back into any one of the equations above, we're going to get that, oh gosh, sometimes I get lost with these markers. VB final is going to be 0. So this means that these two guys would actually switch their velocities. VB is going to stop right here, while A will oscillate up, stop at some point, and come back down against B. And when that happens, they will undergo another elastic collision where they're going to again switch velocities. So VB will end up moving to the left with a velocity of -1 meters per second, and A will end up at rest. And they undergo two completely elastic collisions. That's kind of an interesting problem.